Hello, today we are going to learn about aromatic compounds. So, coming to the aromatic compounds, the aromatic compounds are the ones who have high degree of unsaturation. High degree of unsaturation. One of the most common aromatic compounds is benzene in organic chemistry. So, benzene has a structure like this. Or like this. So, the formula representation of benzene is C6H6, and these are the resonating structures of benzene. So the overall structure of the benzene is something like this. So considering the resonance of both the resonating structures, we come to a final structure, and this is the structure of benzene. And the common representations that we use are generally the resonating structures. The resonating structures do not have any existence in reality, but they are momentarily changing. So they are when you observe the structures, they are momentarily changing. So let us come to benzene. I just spoke about the benzene and the benzene structure. So after talking about its structure, let us talk about its commercial preparation. How does the commercial preparation process? Commercial preparation of benzene take place using coal. So for coal, we use destructive distillation, and then we end up getting coal gas plus coal tar in the process of, and then coke and ammonical solution. In the process of benzene, destructive distillation of coal, we get the following. These four products. Those were the coal gas, then coal tar, coke, and then ammonical solution. And now the coal tar is will be undergoing destructive distillation, and we'll be getting light oil plus mid oil, the destructive distillations, and heavy oil, and then anthracene oil, and some residue which we wouldn't care of. And now from this, among these products, we use light oil next, and then the light oil will undergo fractional distillation. Remember this is fractional distillation at this time, not the destructive distillation. And then we get benzene. So we have arrived at the required product, that is benzene. So this was the commercial preparation process of benzene. Now coming to the laboratory preparation. The way it is prepared in the laboratories. We use sodium benzoate. I mean, this is one of the common processes which we would have learnt even in the hydrocarbons using the benzoates. Sodium benzoate. And NaOHCaO. And the second one is benzene sulfonic acid. On reaction of it with dilute H2SO4. And the next process is phenol along with benzene and heating. We'll be going through this in detail in the following period of time. So until then, and one of the very common process is this, using ethane. This is known as aromatization. We use red hot iron and the other process is using diazonium salts. This is a diazonium salt. It is carrying plus charge and negative charge, and on reaction of it with H3PO2 in presence of an alcohol, that is ethanol. And the other process is N-hexane. You must know what is N-hexane. One, two, three, four, five. Okay, let me do it properly. Okay, this is N-hexane. On reaction of N-hexane with Cr2 O3 Al2O3 and on heating, all these reactions give benzene. All of this give you benzene. Okay, and even this reaction gives you benzene. So these were the 6 common methods of preparation in laboratory. So revising through it, we use sodium benzoate along with NaOH, that is sodium hydroxide, and calcium oxide. We get benzene. And the next one is benzene sulfonic acid. We acidify it and then we get benzene. We'll be learning the mechanisms very soon. And the other one is by using the red hot iron along with ethylene. And the fifth process is using diazonium salt. This is a diazonium salt. I forgot to mention it. Okay, and the other process was, the last process was using N-hexane. So going further into the details of benzene, benzene has 4 degrees of unsaturation. So, talking about the characteristic reaction that benzene follows. That benzene undergoes is EAS. When I elaborate it, it is electrophilic aromatic substitution. Okay. So what does that mean is there is benzene. Benzene okay, this is benzene. Okay, this is benzene. This benzene, along with an electrophile E plus, you get I'm using this for my so that I need not draw again. You get this. On talking about the mechanism of this electrophilic aromatic substitution, we have benzene of this form. Okay, this is benzene. Then we have an electrophile, and there will be a slow reaction carrying on. The benzene is very stable. It is having 2 resonance structures, and the bond order is almost, it's more than 1. The bond order of benzene is more than 1, so it is very difficult to carry out a reaction to break in between and carry out the reaction. So as any reaction would require bond breaking and bond joining process, so joining of the bonds, breaking down and joining of the bonds, or creation of new bonds, so it makes it quite difficult for benzene to react. So due to which the process turns out to be a bit slow. And the slow process doesn't mean that the reaction doesn't even happen at all, but it also happens, but it happens a bit slowly. So this okay. Okay, this is benzene. Now this E plus will go and attack. Let me show you the attacking stuff. It will go and attack over here. I mean, it can happen in any place. So we'll take this as a convention. So it's a convention that I'm taking for myself. So it would be a bit easier for me to represent this stuff. E, and there's H, as you all know, because the benzene structure, okay, I haven't shown, I guess. Yeah, I'll show it. The actual structure of the benzene, I think you would know that this is the actual structure of the benzene. These are the carbons, and there's H, there's H, there's H, there is H, there's another H, there's another H. So this is benzene. This is the actual structure. Okay, the carbons are represented by this tips, by those type of tips of the bond line structure, and the heads are not represented. So now I'm considering the representation of the hedge because it plays some important role in this type of mechanisms. Okay, so we have this type of resonance. For this structure, so you have already this type of resonance, and this bond has to be broken because carbon can have at max 4 bonds attached to it. So this carbon is having 4, like 1, 2, 3 and 4. There are 4 bonds. Carbon has its valency as 4, so that's why there will be no this bond. So this bond will be broken, this bond, this double bond. Okay, and now and this is known as arenaeum ion, and there will be a plus charge because of the bond breaking over here. This E plus has attacked this benzene at this point. At this point it has attacked, so this bond can be written as this one as well, so like minus and plus, which should represent a bond. So assuming that here it's minus and here it's plus, when this E plus attacks this minus point, when this E plus attacks this minus point, obviously this plus is going to remain in the compound. It's going to remain. So I'm representing it as plus over here, and we know that these now this product this can resonate. This is a transition state. I mean, this is a kind of intermediate. I don't call it a transition state. This is an intermediate, I can call it. So we can consider the resonance among this with this. So let me consider resonance of this. So considering the resonance, we do have this. Okay, I'll show you the changes that will happen. Just a second, let me draw all the structures. Okay, you see this. Let me redraw everything, considering whatever the changes that I'm supposed to make. The structure will remain as it is, the first one, because we are considering resonance from there. Okay, there's plus over here, considering the resonance. So this is also one of the resonating structures that you can find. This E and H remain still the same, and considering the other resonances, I'm just representing in blue so that you'll be able to differentiate how the bond breaking is happening and the resonance is happening. Not the bond breaking, the resonance. Okay, I'll represent it with blue. Okay, these are the resonating structures of this arenaeum. This is okay. This is named as arenaeum ion. Arenaeum ion. So this arenaeum ion has how many resonating structures? There are 3 resonating structures. Now, the final structure that we can assume to take is, the actual structure that we is something like this. The plus is distributed among all these bonds, and there's H, and there's E, that is the electrophile that has attacked. So this is known as sigma complex or arenaeum ion. Now in the step 2, we have the sigma complex. This is step 1. In the step 2, okay, so we have this, and then so we have a nucleophile that comes with along with the acid. So this nucleophile takes up this H. This H will be taken up by this nucleophile, and then we get this. There was plus over here, H and U. So we saw that. So the conclusions are, it's a two-step process. And the rate is quite slow. A rate of reaction is 2 benzene, concentration of benzene, and then concentration of E plus. So we find the rate as 2 because 1 plus 1 equal to 2. So, and it's a bimolecular reaction because it involves involvement of two molecules. As I told, the rate of reaction is rate constant into concentration of benzene into the concentration of electrophile. So this turns out to be a second order reaction. Second order reaction, and I'm talking about the kinetics of this reaction. So this involves two transition states. You have seen the transition states that being shown, and then the reaction is exothermic reaction. We can so if I show the potential energy and the reaction coordinate, potential energy and reaction coordinate graph, this is P, let's say, as there are two transition states, you'll have two peaks. Okay, so you have somewhat like this, and then you reach the transition state 1, and then you reach transition state 2 at a lower energy, and then you've reached the final product, which is much lower than the initial product's energy. So initial product's energy is at this point A. This is B. Let's say this is transition state 1, transition state 2. The energy of these are the following. This is C and this is D. And we are also supposed to note that rate of this reaction, yes, E is going to be proportional to stability of uranium ion. So the rate depends on the type of groups. Rate depends on, okay, 1 second, there's some problem with the pencil. Charge it. Okay. Rate of reaction depends on the type of groups, that is electron releasing group, or the electron withdrawing group. So the common electron, as the rhenium ion is carrying positive charge, so the if the initial reactant has more electron releasing group, so the this positive charge of the this positive charge that is localized this positive charge that is localized will be stabilized due to the electron releasing groups, so due to which the reaction is said to proceed faster. So more the stability, so better the products. We need everything in terms of, we talk mainly in terms of stability and the potential energy. And you also know that the potential energy is going to be inversely proportional to the stability. Like if a compound is more stable, so it is going to contain the least amount of energy, and if it is going to have the high amount of energy, so it's unstable.